Hi students, today we are going to discuss on the horizontal oscillations of a spring mass system, which is otherwise called by the name linear harmonic oscillator. What is a spring mass system? A mass like a wooden block is attached to the free end of a spring whose other end is attached, fixed. So this is the mass, this is the spring. So it is called spring mass system. Now what do you expect if I apply a force on the x-axis and pull this load? When this load is pulled on the x-axis, it will be stretched along the x-axis. So that is shown in the second diagram. So the applied force F applied is acting along the x-axis. So the displacement also is produced along the x-axis, okay? But after stretching the load, if you leave the load, if you remove the applied force, what next is going to happen? Will the wooden block rest there itself forever, permanently? No. So the next moment you leave the wooden block, it will try to come back to its initial position first, okay? So which force is bringing the wooden block back to its original position? That force only is called as the restoring force. So here I have shown here, this is the direction of the restoring force. When the applied force is acting along the positive x direction, the restoring force will be acting along the negative x direction, opposite to that of the displacement. Yes, my dear students, do you remember the definition of simple harmonic motion? The motion of a body is said to be simple harmonic when the applied force and the displacement are oppositely directed and also proportional to each other. Okay, so this is the diagrammatic representation of a spring mass system, which is also called as a linear harmonic oscillator. Now, after the wooden block is stretched and left, it will come back to the initial position. It will be restored back, again it will be compressed and again going back to the original position. Then again the spring mass system, the load is going to oscillate about a mean position. Okay, what next we are going to do? We are going to derive an expression for the time period of oscillation of the wooden block and also the frequency of oscillation. Okay, now I will write this restoring force, is also represented by simply F. So I will write restoring force, that is F. This F is proportional to this X, or F is equal to minus K times X. Okay. So F is also from Newton's second law. From Newton's second law, we can also write this force must be equal to the mass of the wooden block m into its acceleration, that is d square x by dt square. When x is the displacement produced on the wooden block, if you differentiate the displacement once, dx by dt is its velocity, and the second derivative of the displacement x, that is d square x by dt square, is its acceleration. Okay, so I can also write F is equal to m into a. So this is equation 1 and this is equation 2. So I have written two equations for the restoring force F. I am going to equate the right hand sides of equation 1 and 2. So from equations 1 and 2, I equate the right hand sides. So mass into acceleration is equal to minus k into x. Okay, now you tell me what is k? What is k here? There is a constant here, is it not? This constant k is called as spring factor or spring constant or force constant. Is it not? So here I will write what is k just below the next equation. So from this I will write acceleration is equal to what? Minus k by m into x, and this is the third equation where k is called as a spring constant or force constant. Okay, spring constant, or it is also called as a force constant. It is an elastic constant and its unit is Newton per meter. Force constant is different as a force per unit displacement. We have studied in the earlier videos. Okay. Now this third equation, I will highlight the third equation. The acceleration A is now equal to minus k by m into the displacement x. This negative sign indicates that the acceleration, okay, and the displacement are oppositely directed by the definition of SHM. Okay, now from the definition of SHM, how did we define SHM? It is a type of motion in which the restoring force and the displacement are proportional to each other and also they are oppositely directed. Is it not? When force and displacement are oppositely directed, then acceleration and displacement must also be oppositely directed. Therefore, from the definition of SHM, I can write this acceleration is also equal to minus omega square into x. So this is at the beginning of the chapter, we defined simple harmonic motion like this. Is it not? Where omega is called angular frequency. And angular frequency is 2 pi times the actual frequency. Okay children, now I am going to equate the right hand sides of equations 3 and 4. What is equation 3? Can you read? A is equal to minus k by m into x. Now you read equation 4. What is A equal to? A equal to minus omega square into x. So equating, okay, equating 3 and 4, I can write minus omega square x. Okay, minus omega square into x is equal to minus k by m into x. Okay, minus k by m into x. So I can cancel x on both sides. This minus sign also will be cancelled. So omega square will be equal to k by m. This implies what is omega is equal to square root of k by m. So I will highlight this also. This is very important for us. Did you understand? The angular frequency omega is now equal to what? Square root of k by m. Now next step we are going to derive an expression for the period of oscillation. Okay, period of oscillation. Therefore period, okay, t is equal to 2 pi by omega. So this is equal to 2 pi divided by square root of k by m. This is also equal to 2 pi into square root of m by k. So this is the expression for the period of oscillation of the spring mass system, and this is equation 5. Understand that? So t equal to 2 pi root m by k, very important equation. See, this m is called mass of the body, okay, or mass of the wooden block. It is called inertial factor. Is it not? Have you studied in the beginning of the chapter or not? M is called mass of the body, that is called as the inertial factor. So denominator k is called a spring factor. So I can also write it, t is equal to 2 pi into square root of inertial factor, okay, inertial factor divided by what is k equal to spring factor. It is called as a spring factor. This is also another way of representing the period of oscillation. Okay children, if you take the reciprocal of the time period, what expression do we get? Yes, that is the frequency of oscillation. Okay, so frequency, next step is what? Frequency of oscillation. It is a reciprocal, is it not? So F is equal to, you can use different symbols, F or nu, okay, or small n, any symbol. So this is equal to the reciprocal of the time period. So if you take the reciprocal of the time period, this constant will become what? Yes, 1 by 2 pi. Good. So this is equal to what? 1 divided by 2 pi into square root of k by m. Is it not? So square root of k by m. So this will be the equation number 6. The last equation. Now these equations for period and the frequency is true only when the amplitude of oscillation is very small. Understand? You see here, suppose if the string or if the mass attached to the spring is stretched very harshly by applying a very large applied force, permanent deformation may also take place in the spring and the mass may not come back to the original position. So that will become non-linear oscillation. Understand? So under what condition the oscillation will become linear? Only when the amplitude of oscillation, that is from the mean position, the oscillation should have what? Yes, small amplitudes. Suppose if applied force is very large, under that condition the applied force is extremely large, then permanent deformation may take place or it will become non-linear oscillation. Okay, so only for small amplitudes the spring mass system can be considered as a linear harmonic oscillator. Okay children, have you all understood well? Fine.